Let's work now on example D on a transistor with a beta of 200. But before doing that, let's review some things. Previously, in the past two examples, the transistor was either cut off or was saturated. That means that the bias circuit was not doing its job properly, which is to ensure the transistor is in its linear mode of operation, that the BE junction is on and the BC junction is off. That means the current in the base is positive and that the collector in an NPN transistor is higher than the base. How do we design properly that a voltage divider common emitter bias circuit? Let's begin with the value of the voltage source. The power supply available, let's say, it's given to us as 15 volts. In the load line of IC versus CE, the characteristic is a straight line that we've named the load line. That cuts down here in the VCC value of the power supply and up here in the value that will be for a configuration like this one, the value of the power supply divided by the sum of those two resistors, VCC divided by RC plus RE, approximately, but that is right. We have seen also that we would like to be exactly in the middle of this load line segment right here. We want the quiescent point. Here's where we want the VCE quiescent, and here's where we want the collector current and the quiescent point, IC cubes, and there is an extra V in here. So that means that in this case, if this is 15 volts, we want the voltage here to be half of 15 volts, approximately 7.5 volts. Now, the rule of thumb of design of a circuit like that, now I realize that those capacitors are getting in the way and they are doing nothing in the design of the bias circuit, which has to do exclusively with a DC circuit. Let me eliminate them so they do not get in the way. Well, the rule of thumb I was saying was to take the other half of the 15 volts, the other 7.5 volts, and distribute them between those two resistors in such a way that I have 3/4 of them allocated to the collector resistor and the other quarter down here. That means this would be 7.5 divided by 4 times 3, and this would be the other 7.5 volts divided by 4. And that is the approximate voltage that we're going to allocate in each one of 1.9 volts approximately, and 2 volts, and this here would be 5.6 volts. That's right. So that's the distribution of voltages. Now we have to decide what is the quiescent current in the transistor, this value, because that will set what is the maximum swing of the signal up and down around that quiescent point. Let me say for this exercise that I want the ICQ being 1 milliamp. If this is 1 milliamp, of course, the value of the current in the emitter, this one, is going to be approximately 1 milliamp as well. We know that. Then we can make an approximate computation and say, well, if this is 2 volts and the current is 1 milliamp, then RE will be 2 volts divided by 1 milliamps, that is, of course, 2 kilo ohms, and that is how we found this one. And for RC, we do the same computation, 5.6 volts divided by the chosen 1 milliamp current, that is 5.6 kilo ohms. And then we go to the closest commercial values for those. For this one would be 2.2 kilo ohms. And now that we've done that, we want to compute what are the values for R1 and R2. Apart from ensuring that the transistor is in its active mode, this configuration, the voltage divider common emitter one, is so popular because it has one very important feature. You see, transistors, as we've said in the lecture, they don't have a predictable beta. I mean, when we purchase them, we don't really know what beta we're going to get for a given transistor. Once we have them, that beta can even change with temperature. We want to design the bias circuit so that the Q is whatever we want it to be, regardless of the beta. How do we ensure that? Let's review this bias circuit on this side. What does it look like? Well, what we have there are resistors R1 and R2 in series connected to the VCC and to the reference node. And here we have this resistance RE, but how it looks from the side. And it looks actually as RE multiplied by a big factor, because the current that flows through RE is going to be 1 plus beta. So it looks like a resistor much bigger than it actually is. If we want this voltage to be completely independent of the beta of the transistor, what we want is to make this resistor much smaller than this one, that we can neglect the current in the base. We can say the current in the base in this computation will be negligible if we choose R2 so that it's much smaller than beta RE. So we choose a rather smallish value for beta, let's say 100 RE. The rule of thumb in industry then is to choose R2 less than 10 times RE. And by doing that, we ensure that we can compute the voltage VB, this one, without actually having to take into account the transistor, only as a voltage divider. And that is what we're going to do. I will compute R2 as a number that is less than 10 the value of RE. 10 RE would be 22 kilos. I want less than 22 kilos. I'm going to choose 10 kilos. R2 will be 10 kilo ohms, and that's how I choose that one. But now that I found this one and that one, how do I find R1? Well, another approximation. I know that the voltage here, VE, has been approximated to 2 volts. Actually, right now, 2.2 volts. Well, 2.2 plus 0.7 volts here in linear mode of operation give me the voltage and the base, the voltage here. And that is 2.9 volts, of course. But then think of it. Now we know the voltage here and we know the value of this resistance, which is 10 kilo ohms. Of course, we can compute this current I2, which is 2.9. Let me write here. I2 is 2.9 divided by 10 kilos. That is 290 microamps, which is bound to be much larger than whatever base current we may have, at least 10 times bigger than that. Well, one more assumption, as we have made things so that the base current can be neglected in front of I2, we will approximate I1 to I2. We say this is approximately I1, and then we can say that this resistor at the top has the value of 15 minus 2.9 volts divided by that current. 15 minus 2.9 divided by those 290 microamps. And that is 42 kilo ohms. And that is the resistance here. Of course, now we have the task of finding commercial values for all of those resistors and recompute that. And we should rest assured that this circuit is going to keep the transistor not only in its linear mode, but also it will guarantee some room between the cutoff mode and the saturation mode for the signal to swing as widely as possible.